Question 5. Tulbutol is used in some medicine, and figure 1 is the structure of this tulbutol. Okay, part A. Tulbutol contains a benzene ring in its structure. Describe and explain the shape of benzene. In your answer, include the bond angle between the carbon atom, hybridization of carbon, and how the orbital overlap to form the sigma and pi bonds. Okay, so first you need to know the hybridization of the carbon in the ring is sp2. So means one s orbital and two p orbitals that will mix and undergo hybridization form the three identical sp2 orbitals. Okay, this one, and it will form 1, 2, 3 sigma bond. And these sigma bond, they are the sigma bond between the C and H, C and C, and another CC. So there will be one unhybridized p orbitals here, and this one will form the pi bond. Okay, for example, this carbon has unhybridized p orbital. This carbon also has unhybridized p orbital. These p orbitals, they will overlap and form the sigma bond. So this is how the overlaps happen. And the bond angle, because all these carbon, they are sp2 hybridized, so it will be a trigonal planar geometry for all carbons. So the bond angle between the carbons, it will be 120 degree. So these are all the informations that you must know before you answer. Okay, so now let's start this. Okay, all carbon in benzene ring, they are sp2 hybridized and trigonal planar shape. Okay, so this one I already told you, sp2 hybridized and trigonal planar geometry. The whole benzene is hexagon ring planar, so it's hexagon the shape, right? And the bond angle between the carbon is 120, as I told you just now. Okay, because all the carbon is sp2 hybridized. Okay, sp2 orbitals from carbon H-on overlap to form the sigma bond. So means the carbon, let's say this is one carbon, this is another carbon. So the hybrid orbitals will undergo H-on overlap and it will form the sigma bond, right? So this is how the sigma bonds form. And of course the p orbitals, as I told you just now, it will undergo sideway overlaps between the carbons, and therefore it will form the pi bond. Part B. In the synthesis of tulbutol, the first step involves the formation of chlorobenzene, which the benzene reacts with chlorine in the presence of the catalyst AlCl3. So this is the reactions. Must have chlorine with the catalyst, then chlorobenzene will form. Write an equations to show how the chlorine reacts with the catalyst to generate the electrophile. Very easy. So the chlorine reacts with the AlCl3. The AlCl3 will get one chloride from these chlorine molecules, and it will form AlCl4 negative. So at the same time, it will form this chlorine ion. So Cl positive. This is an electrophile that reacts with benzene ring. Then part 2, complete the mechanism between the benzene and the electrophile, means the chlorine ion. So must draw one arrow from benzene ring, point to the ion. After that, draw the intermediate. The intermediate, you must draw the hydrogen, the CH bond here, and must draw one arrow from CH bond, point to the ring, point into the ring, to show that these electrons, this pair of electrons, will move to the benzene ring and restore the aromaticity. And of course, in this intermediate, you must show the partial positive, the charge here. So just draw a curve and a positive charge. After that, it will form this chlorobenzene and of course the H plus, the proton. Okay, part C. This question, this part is quite complicated because it has a few possibilities. Okay, for this one, the synthesis involved the reactions of chlorobenzene, mean this one, with this compound. So this compound you have to understand means the ClCO, CH2Cl, this one. So it can form two different electrophile when we use the AlCl3 catalyst. Means this one, okay, if you react with the catalyst, then it will form this acylium ion, or this part will react with the catalyst to form this alkylium ion. So means two possible electrophile can be formed from this compound with the catalyst, right? So it means when this electrophile form, then it will undergo acylation, and when these electrophiles form, then it will undergo alkylation. Okay, so for this figure 5.4, the product that form is Q, and this one obviously is the acylation product, means it's a reactions between the chlorobenzene with this acylium ion to form this Q. And of course, if you form others product, the alkylation product, means this ion or this electrophile will also react with chlorobenzene and form this alkylation product. Okay, it's slightly different, see? This part and this part is different because it involves different electrophile, right? Okay, so now part 1, name the mechanism for the step 2. Step 2, because we know that it's undergo acylation, and the mechanism is electrophilic substitution. Okay, draw the structure of an isomer of Q formed as the organic byproduct of the reaction 2, means you can draw this one, the alkylation products. Right, so this one, or you can put because the chlorine is 2,4 directing, means the substitution can happen here or here. So the byproduct also you can put at the 4th position. It's okay. So means the alkylation can happen at the 2nd or the 4th position, right? So you can give this one or this one, or you can give the acylation product at the 4th position. So these are the possible answers. Okay, part 3. The reactants used in the step 2 contains acyl chloride, alkyl chloride, and aryl chloride. Okay, acyl chloride, so we know that it must have the C is bonded to these the oxygen and the chlorine, right? So alkyl chloride is just the carbon, right? Is bound to this one means the chlorine only, and of course the others hydrogen and alkyl group. Okay, so this one is the aryl chloride, means the chlorine bond to the benzene ring. So state and explain the relative ease of the hydrolysis for this acyl chloride, alkyl chloride, and aryl chloride. Okay, of course, the one that easiest to undergo hydrolysis is acyl chloride, because this carbon is more partial positive or is more electron deficient, because this carbon is bonded to 2 electronegative atoms. So these 2 atoms, if you withdrawn electron, and this carbon, it will be more electron deficient. Therefore, it's easier for these carbons to get attacked by others or react with others. So therefore, the easiest to undergo hydrolysis is the acyl chloride, okay, followed by the alkyl chloride, and the last one, of course, is aryl chloride. Why aryl chloride is the one that hardest to hydrolyze? Because of the double bond character. So we know that the chlorine has a p orbital, and it will overlap with the pi electron system in benzene ring here. And after the overlapping, the lone pair on chlorine can delocalize in the benzene ring. Okay, means it can form the double bonds from time to time. And when the double bonds form, and this one is actually harder to break because it's stronger. So therefore, it's harder to undergo hydrolysis. So that's the things that you must know how to answer, right? Okay, so this one is okay. So let's start with the explanation. Okay, so the carbon in this CCl in the acyl chloride is more electron deficient. Okay, as is attached to the oxygen and this chlorine atom, right? So means the carbon, okay, in this acyl chloride is bonded to the chlorine and another oxygen atom, so it's more electron deficient. And for the aryl chloride, okay, this one is for the acyl chloride done. For the aryl chloride, the CCl bond, okay, is formed the partially double bond, okay, like this, which caused by the lone pair on the chlorine delocalized in benzene ring. So because of this delocalization, okay, then it's formed the double bond, and the CCl bond now is stronger. It's hard to undergo hydrolysis. So normally we will just discuss the easiest and the hardest one, right? So the easiest one, again, the carbon is more electron deficient because it's bonded to the chlorine and oxygens. And the aryl chloride, okay, the bond is stronger because it's formed the double bond, okay, partially double bond character. Okay, part D. So the tulbutol is produced from the Q, as shown in this 5.5, figure 5.5. So the Q, okay, undergoes step 3 and step 4, and eventually form this tulbutol. Okay, so from here, the Q, okay, and we compare the Q and the tulbutol. So we notice that, okay, this is the group that difference, and this one, right? So means after the step 3 and step 4, so these two group means this carbonyl group and this chlorine must change. So we know that, okay, for the step 3, this chlorine must substituted by the amine, So the amine that substitute the chlorine, it must be this one. So if you try to draw the structure or give the formula, so it will be the CH3 bracket 3, okay, because 3 out methyl group, okay, C and H. So this is the group, and we just need to add another hydrogen here. Then this is the amine that we use to substitute the chlorine. Okay, so therefore the chlorine substitute by this amine. Okay, so from this part we can deduce the amine that used. Okay, after that, so it will form Z, and this Z will be the one that form the alcohol. So means this carbonyl group now will undergo reduction. So you need to add 2 hydrogens there, add 1 hydrogen and another hydrogen here to form this alcohol. So means the step 4 will be a reduction step. So this is how you deduce the answers, right? Suggest a reagent and condition for step 3 and 4. Okay, draw the structure of Z in the box. Okay, so step 3 again, we use this amine in ethanol, heat under pressure. Okay, remember this is the primary amine as well, because NH2 with 1 alkyl group. Okay, so after that, this is a Z that form, means the chlorine substitute by this group, right? So after that, the step 4 means the reduction. We can use lithium aluminum hydride or sodium borohydride. So the Z here will add 1 hydrogen, here carbon will add 1 hydrogen, double bonds gone, right? So it will form this, okay, tulbutol. Okay, this is the step 3 and step 4. Okay, part E. The synthesis produce 2 enantiomers of the tulbutol. Define enantiomers. Enantiomers actually is the optical isomers, the pair of optical isomers. Okay, so which means it's the stereo isomers that are non-superimposable mirror images, or the stereo isomers that rotate the plane polarized light, okay, to in the opposite direction, which means when there is a polarized light, it passes through the, let's say, one stereo isomer, let's say to positive 10 degree, the others must be the others enantiomers must be negative 10 degree. Okay, part 2. Suggest one disadvantage of producing 2 enantiomers in the synthesis. Okay, so disadvantage is because after it's formed 2 enantiomers, we have to separate it, because sometimes only just 1 enantiomers is effective. So therefore, we need to separate the optical isomer to get the pure active isomer for certain disease. Or we can say that it's reduce the biological activity of active enantiomers. Okay, suggest a method of adapting the synthesis to produce single enantiomers. Okay, we can always use chiral catalyst to save time, right? And it's more specific. Okay, part F. 1. Predict the numbers of peaks that were seen in carbon-13 NMR in this the tulbutol. Okay, so just follow the numbers that I put here. We're going to look for the equivalence carbons, because equivalence carbon always form the similar signals. Okay, let's say now we start from here. These methyl, they are actually equivalents. So it will produce the similar signals. So it will form 1 signals in carbon NMR. And this is another type of carbon. So 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will form 10 signals. If let's say the chlorine is not here, then it will be 5, 6, 7, 8. 8 signals. It depends on how many equivalence carbons there. Okay, so for these tulbutol, the numbers of peaks will be 10. Okay, so this one is about the proton NMR. The proton NMR spectrum of tulbutol is dissolved in D2O. Shows peaks in the 4 different types of proton environment. So you have to know that, okay, when we use D2O as a solvent, the OH and NH peaks will disappear, because it will undergo proton exchange with the D. So it won't really give any signals whenever the compound dissolve in D2O. Any signals about OH and NH. Okay, so that's why these OH will not appear in the proton NMR. Okay, and another information is given. The peak for the CH2N means this one. CH2N, this one. This is the doublet in the chemical shift range 2 to 3 ppm. So means this one will couple with this proton to form a doublet, and this doublet is around 2 to 3 ppm. Okay, so this one already given, no need to discuss. Now you need to discuss the other 3 peaks in the proton NMR of the tulbutol. So means it's want you to discuss, okay, not this, so it want you to discuss this, and this, right? These 3 peaks. Okay, so you have to discuss chemical shift, environment of proton, splitting pattern, and numbers of hydrogens responsible. Quite complicated. So you just follow step by step. Okay, now we try to discuss this one first. This one. Okay, so for this methyl, right, these 3 methyls, they are equivalents. That's why it will produce a singlet. So because this and this proton, okay, it will not really couple with others proton because the adjacent carbon has no protons to couple with. Therefore, it will just form a singlet. Okay, so this is a splitting pattern. Okay, with 9H, so total 9H, and this chemical shift is around 0.9 to 1.7 ppm. Its proton environment is alkane. So you just refer to the tables given, this one, the first one. So it will be the environment of proton is alkane, and chemical shift for this 3-methyl is 0.9 to 1.7 ppm. Okay, so this one is for the first signal that we discussed. Okay, now let's move on to the second signal. I mean this one. So this proton will not couple with this proton because the C with O, this is O, right? So this one will not couple. Okay, this proton only will couple with these 2 proton. So it's 1 plus 2. So you see a triplet there. So there is a triplet with 1H, okay, because here is just 1H, okay, at 3.2 to 4 ppm. Okay, because this CH is next to electronegative atom, right? So therefore it's follow this one. Alkyl next to electronegative atom, so is referred to this one, right? So when the proton, right, next to the means CH or CH2 is next to the O, right? So the chemical shift is 3.2 to 4. Okay, so therefore this is the answer for second signal. Again, there is a triplets with 1H, triplets with 1H at 3.2 to 4 ppm, and the environment of proton is alkyl next to the electronegative atom. This one, alkyl next to electronegative atom. Okay, the last one, there is a multiplet with 4H, means this, and this, because there is a CH here, 4 protons here. So whenever it's more than 4 or more than 4, so we just put multiplet. There is a multiplet with actually the 4 peaks, right? Okay, we call quartet, but for the benzene ring normally we call multiplets. With 4H, okay, at 6 to 9 ppm, and its proton environment, okay, is a proton attached to the aromatic ring. Okay, so this one again you have to refer to the table. So proton environment is, okay, attached to aromatic ring. Chemical shift is 6 to 9. So this is the last signals. Okay, again there is a multiplet with 4H 1, 2, 3, 4, okay, at 6 to 9 ppm, and its environment of proton is attached to aromatic ring. This is the proton environment. Okay, so that's all for this question. Thank you.